Yeah, good morning, good afternoon, good evening, wherever you are at this point in time. My name is Marco Bonov. I'm the ICDP Executive Director, and I am based at GFZ in Potsdam. I would like to start with thanking the organizers for inviting me to give this presentation. And the title of my presentation is Fault Zone Drilling and Monitoring. Where do we go from here? And likely in contrast to most of the other in-depth science talks that you are hearing during this conference, I'll try in the next 15 minutes to give you a very brief overview, review, and also perspective on the topic of fault zone drilling and monitoring. And I'll also include a few remarks on sort of best practice on how to realize such projects. Now, as a general motivation, on the one hand side, no matter in which way we are going to supply mankind with energy in the future, be it still conventional, unconventional hydrocarbon, be it renewable / geothermal, hydroelectric, or hydrogen, and in this context storage, we will continue to use the geological underground in the future. And this comes along with increasing anthropogenic seismic hazard and risk, and also public accepted issues. And I don't need to name the key projects here. You all know them, such as Pohang, which is why we are here, Basel, Central Eastern US, and for example, Blackpool in Great Britain. Now, on the other hand side, there is a rapidly growing population concentrated in population centers that are co-located with active faults. And these are primarily, but not only, continental transform faults, megathrust faults, but also blind faults. And this development clearly results in a dramatic increase of natural seismic risk along most active plate boundaries. And again, key examples here are the LA Basin, San Francisco Bay Area, Istanbul, Tehran, Quito, Port-au-Prince, and this list can easily be extended. Now, this situation calls for action, and as what I would call action 1.0 here, which will not, which we won't focus on in the following, but which is clearly most important, is to improve resilience through better construction of buildings. That's the most straightforward way, but it's extremely expensive. It can be done for natural risk. For anthropogenic risk, it's more difficult because we don't know where these risk spots will pop up in the future. I'll focus on what I call action item 2.0 here. That is to aim at a better understanding of the underlying physical processes in order to progress towards mitigating both natural and anthropogenic seismic hazard and risk. And mitigating here is a challenge, but it's only the first step, because we're all ultimately aiming at hopefully controlling, or on the far end, even avoiding these types of hazard and risk. Now, this is a clearly ambitious goal, given the complexity of the system and the fact that we are dealing with processes that happen kilometers below our feet with no direct access other than a few boreholes. And for example, in comparison to weather and climate risk, this is clearly different because there we have the full view on the system. We have a much better understanding in terms of processes and also the math and physics. That's not yet the case for the seismic part of the game. We also clearly need, and this has been demonstrated especially over the recent years, we need lab and mesoscale research as well as numerical modeling where we have controlled boundary conditions to provide us with key observations and observables. And ultimately, the key observations that we need to get ground truth that can only come from either sampling through fault zone drilling or observing through fault zone monitoring the processes in situ, using in part continental drilling as a tool. So in this talk, I will give you a very, very brief history of recent and also ongoing ICDP fault zone drilling and fault zone monitoring projects. I will give a few notes on related challenges as well as novel strategies and attempts. And finally, last but not least, I'll give you a few remarks on the role of ICDP in this respect. Now, this is a no-go slide, I know. It basically shows a summary, a brief overview of all the previous and ongoing fault zone drilling and monitoring projects. And I have no time to go into detail to any of them. And you've seen the talk by Steve Hickman on SAFEHOT, which is clearly a key project in this respect. Now, fault zone drilling, I would say, originated with KTB, where there was a very deep drill hole into a non-active ancient fault system that also served as the nucleus for the ICDP. Then there have been a number of important projects in the South African gold mines where drilling was performed and monitoring in gold mines at more than 3 kilometers depth. There were successful projects in Ojima, drilling into the 1995 Kobe earthquake rupture. Same for Chilumpu, the Chichi earthquake, which was drilled. Both also had an extensive monitoring and also active experiments involved. SAFEHOT, I'll mention in a minute regarding the HRSN on the ICDP project. SAFEHOT, you've heard a lot already. Then the Alpine fault, drilling into a transpressive fault where a magnitude 8 earthquake is pending. This also involves a huge monitoring component. The Venturan fault drilling project in China, drilling the 7.9 rupture of the Venturan earthquake 2008. JFAST was a key project, IODP-driven drilling into the magnitude 9 megathrust rupture offshore Japan. And then the GONAF project in Turkey, which was the first real downhole monitoring experiment funded by ICDP. And the Koina project is important, I mentioned that in a second. And then we have two ongoing projects, the STAR project in Italy and Daphne in Sweden, both involving a huge amount of fault zone monitoring. So the main philosophy of all these projects is to study earthquakes and their physical processes at active faults on the long term through either drilling into the fault or performing high resolution fault zone monitoring. And the classical project for fault zone monitoring is the HRSN, High Resolution Seismic Network at the SAFEHOT at the Parkfield location. This was the first borehole-based seismometer array that was deployed in the mid-80s, which is actually still in operation. I would actually tend to call it the mothership of borehole seismology. It was the first project of this kind, and it was really a success. These concepts have been further evolved over the last decades, and of course, the most extensive borehole-based seismic network now in the world is the HyNet in Japan, with a dramatically high number and a real great data set, allowing to tackle the challenges in better understanding the physical processes driving earthquakes. Again, not too much time for scientific details here, but as you learned already, the SAFEHOT project tackled most of the key questions, which is the mechanic of faults, the role of faults as fluid barriers, also relevant for fluid-rock interaction. One key is learning more about partitioning of deformation, which branches of the faults are active at which time, and why do we have this interaction. In the same context, better learn about locked versus creeping behavior of faults. Then fault zone sampling is key. It's very important to learn more about the composition of the fault core, but here we always have the difficulty that we have only pieces of information from a very local spot, and the question remains how representative this information is actually that we're getting. and many more, including fault zone imaging, improving hypocenter precision through getting near or closer to the source, and also having better azimuthal coverage and lower detection threshold. So there are a number of topics that are tackled in this context. Now, let me very briefly name few of the key projects. When it comes to fault zone drilling, here the current successor of the SAFEWORD project clearly is the Koina deep drilling project, where the aim is on the long term to drill into the rupture of a 6.3 rupture. That was a large earthquake triggered by a water dam. There's a lot of seismicity in this, in part including 20 events of magnitude 5 and so on. So this project is following the successful KTB and SAFEWORD procedure, with a pilot hole followed by a main hole, and the first step along an intense part of the whole game is, of course, baseline information, collecting baseline information and deriving at a characterization of ultimately defining the landing point of a deep well. And here the current status is that a set of shallow, where shallow means 1,000+ meters, shallow boreholes for monitoring is in place. And recently in 2017, also the 3-kilometer deep pilot hole was completed, where now experiments are planned. And this project hopefully will further evolve in the near future, ultimately aiming at drilling at 6+ kilometer depth into the fault zone of the 62 earthquake. Another project that is currently ongoing, which is a perfect combination of fault zone monitoring and eventually fault zone drilling. Here is the Alto Tiberina fault in Italy along the Apennines, where Chiaraluca et al. Have managed to install a high-level microseismic borehole-based observatory, the Tilbu Observatory, and this is currently enlarged through drilling a number of boreholes to install a borehole strain meter array aiming at fault zone monitoring in a combination between the classical seismic monitoring and then also monitoring strain, so slow deformation, which is key to understand the interaction of the whole, let's say, range of deformation that is going on in the underground. Yeah, well, to put all these different attempts in a few sketches, I'll drive you briefly to these two slides where the different concepts are shown. SAFEWORD, for example, a combination, a transform fault of monitoring and then actually drilling into the fault. Fault zone drilling in a normal fault was performed in Corinth. And then you see all these different settings here, including the offshore drilling in Nankai and Tohoku, drilling into a subduction zone, basically on the plate interface. And then there are fault zone monitoring projects and drilling in the gold mines of South Africa clearly is a unique opportunity there, because you don't need to drill down a few kilometers because you're already there, and then can perform drilling as was successfully done in the different projects. And let me point here for one future type of drilling project, let's call it. There are already ideas underway, but this is still on the agenda to actually use drilling and fault zone drilling and monitoring in the framework of triggering or releasing a controlled earthquake. That is something, of course, I know it includes many aspects, especially including public acceptance. But ultimately, this is the way where we need to aim it. So we need to try and we need to aim to control these processes in order to further reduce the seismic risks and make, for example, geothermal exploration more successful. Now, to all these kinds of projects, there are always a number of challenges which are multifold. You always need extensive pre-site studies and baseline monitoring, which takes time and money, of course. but this is needed to have the best characterization of the size. Those projects are always logistically extremely challenging. They're expensive, and ultimately one error can kill it all. That's clearly a risk we're always facing in these kinds of attempts. But there are a number of advantages that clearly overcompensate these challenges. And there, for example, it's the only way really to understand these processes if you go down there. You have much improved fault zone monitoring and imaging capabilities, being in the near field of the processes. Ultimately, you have an improved hypocenter precision and magnitude and thresholds, which is important to reduce the observational gap between lab and field to further investigate earthquake nucleation processes that can ultimately lead to improved earthquake forecasting systems. Now, a brief wrap up. So to understand what's going on, you need to go where it happens, and that is downhole. You need a long breath to realize fault zone drilling and monitoring projects, and I'll refer to this in a minute. And even if successful, fault zone drilling provides info on only one spot, and the question remains how representative this one spot is. You need to combine baseline information with know-how from lab and modeling to design drilling concepts in order to reduce or even close the observational gap. This is especially relevant for earthquake nucleation studies. And on a more organizational level, you need to establish a mechanism for long-term operation of fault zone observatories. That sounds easy, but it's not. You need a mechanism to really ensure long-term funding for maintaining an observatory once it is in place. And so with that, I will lead to the final part of my talk, which is giving you a brief overview and brief insight on what the role of the International Continental Drilling Program is in this context, and also how to realize an ICDP project. So ICDP is an internationally managed and operated earth science infrastructure which facilitates excellent science through continental drilling. We have a twofold approach, which is on the one hand side a top-down approach, which is given through the new science plan that we have just released, defining the core topics of ICDP for the next decade. And vice versa, we also have a bottom-up approach, which has to come by or has to be realized by proposals from the community. So ICDP members are countries, currently 21, that send delegates to the panels running the program. And basically an ICDP membership is the entrance chip to become also a proponent, or in that way, a PI of a project. So in our new science plan that we have just released, we define 4 prime science themes. And in particular, we have also included for the first time a real slot on amphibious projects, where we ask for combined projects involving continental and oceanic drilling. But that's not the topic here, just for your information. So one of these 4 prime themes is geohazards. And here, the key questions are to elaborate on what are the drivers initiating and controlling earthquakes, volcanic eruptions, and mass movements such as landslides. How do we distinguish faults, volcanoes, and potential landslides that present an immediate threat from those with low hazard? And third, last but not least, how do we build a better quantitative understanding of physical processes, allowing us to provide advanced warning time to mitigate the risk of that are associated with geohazards? And that is exactly on the spot of the conference here. So all this sets a frame to foster research on this topic. And now, to get the bit in the ground, you need a long breath. So that's what we would call the ICDP Summit Challenge. ICDP has a very successful commingled funding principle. That means once you have successfully passed the evaluation of a proposal, ICDP contributes to a project with a certain amount of co-funding. This is typically on the order of 20% on average. this is not enough to run the project, that this usually serves as a door opener to acquire additional matching funds from other funding agencies. And while I don't have time to go into the details of the review process, let me show you this figure here, which we call the ICDP Summit Challenge. So typically we start with a pre-proposal that is then reviewed, and if it's encouraged for further development, then you would come with a workshop proposal. Again, if successful, you would get funding to run a workshop with 40 to 80 key scientists in that field in order to work on a full proposal that then ultimately would lead to, if you collect matching funds, to drilling, and then of course a successful drilling project at the end with everything that belongs to that, including sampling, analysis, and ultimately publication. ICDP can look back on a very successful history with 80 plus workshops worldwide that resulted ultimately in 50 or about slightly above 50 drilling projects. And that's where we stand now. We have extensive support within ICDP from the operational support group. We're currently updating the ICDP Primer, which is an extensive best practice brochure for scientific drilling. All this, including the science plan, is available on the webpage. And with that, yeah, I'm at the end of my talk. I thank you very much for your attention, and I'm looking forward, actually live, to get your questions. Thanks.